This little thing decides everything about your print quality. We're breaking it down piece by piece so you actually understand what's happening inside your hot end. By the end, you'll know every major component inside a 3D printer hot end and how they work together to create anything you can imagine. It doesn't matter if you're running an Ender 3, a specialized machine like the Minuteman, or anything in between. All hot ends rely on the same core principles, and those are what we're going to learn together today. Let's start at the beginning. Filament is the first part of the story, because everything the hot end does depends on how this strand of plastic behaves. Flow rate, temperature settings, and print speed all depend on the type of material that you're using. This is the nozzle. The nozzle shapes the molten filament into a clean, pressurized stream as it exits. Most nozzles use a 0.4 millimeter opening, but you can get sizes from 0.2 all the way up to 1 millimeter depending on your application in your printer. Nozzles also come in many materials and designs, but that's a topic for another video. To take the 1.7 millimeter filament and push it through that tiny nozzle opening, we need something that can feed it in with force. That device is called the extruder. The extruder uses gears or rollers to grip the filament and generate the force needed to push it down through the hot end. This setup is a direct drive extruder because it's mounted close to the hot end. The extruder isn't part of the hot end since it doesn't really see heat, but it provides context for how the system works, so we've included it here. Filaments require different temperatures, typically ranging from about 180 degrees Celsius to 280 degrees Celsius. That heat comes from the heat block. The heat block is a chunk of metal, usually aluminum, that contains a heater and a temperature sensor and is used to maintain a consistent temperature at the nozzle for extruding your filament. If for some strange reason we tried to print with just these components, the filament would melt too early and form a blob at the top of the block. Heat travels up through the filament, causes it to soften before it should. We need more components to make this work correctly. If we added a threaded guide to the top of the heat block, this would allow us a path to enter the heat block more cleanly. This would also give us more room for the heat to be transferred into the filament in what's known as the melt zone, but minimal contact area for heat transfer up the line to our next component. You can see with just the heat break in place, we still can't print because we've just moved our over-softened filament point up a bit from the previous test. Now we have to add one of the most critical components in the hot end assembly, the heat sink. To stop heat creep, we use a heat sink. A heat sink is a chunk of metal with fins that help pull away the heat from the heat break. This slows the heat down, but it doesn't stop it completely. You can still see the heat slowly rising toward the extruder. Eventually, that heat would reach the extruder and cause jams or clogging. So what can we do to control that? We add a fan. By blowing air across the fins of the heat sink, the fan prevents the heat from creeping up into the filament path. This keeps the cold zone actually cold, while the nozzle maintains a consistent printing temperature. Because of this, the hot end fan should always run whenever the hot end is heated. If the fan or heat sink isn't functioning correctly, heat creep can still occur, but we'll cover those in the troubleshooting video. Eventually, you'll need to remove this filament. To do that, the hot end must heat up so the softened plastic can release from the melt chamber. If you pull the filament while the hot end is cold, you risk tearing off fragments inside the heat break. That's how jams start, and it's something every 3D printing user eventually encounters. As the nozzle heats, you may notice a bit of filament oozing out, even without extruder movement. That's just expanding pressure. The filament expands as it melts and pushes itself out of the nozzle. Once the hot end is at temperature, retract the extruder slightly to free the filament. As you pull it upward, the softened end stretches and releases cleanly from the melt zone. This is why you'll often see a melted, thinned, or stringy section near the end of the filament. When reloading the filament, the new material pushes into whatever melted material is still in the hot end. That old filament will start coming out of the nozzle first. This process is called purging. You keep purging until the previous color is completely gone and the new one extrudes cleanly. The result of this purge is often called poop. You generate poop at every color change. How long the purge takes depends on the color you're switching from and to. Dark to dark transitions purge quickly, while dark to light transitions and vice versa take a bit longer. Another way to remove filament is with the cutter, which is required for most multi-material systems. The cutter trims the filament to a clean end so automated systems can reliably feed it. In this example, the cutter is above the extruder, but ideally the cut happens as close to the hot end as possible to reduce waste. When new filament loads into the system, it makes contact with the old filament much higher up. This increases the amount of mixed material and nearly doubles the amount in most cases that you will have to purge, which means more waste. Some systems will heat the hot end and manipulate the filament before the cut to reduce waste as much as possible. Other types of multicolor systems, such as nozzle changers and tool changers, have the potential to generate far less waste. We'll cover those in a different video. Now we're almost ready to print. We're just missing one more piece. As filament exits the nozzle, it's molten plastic. If it stays hot too long, it can sag or deform instead of staying exactly where the nozzle placed it. So we add a part cooling fan. Ducting directs air from the fan right to where it's needed, at the fresh extrusion. But this airflow also hits the nozzle, which can make it harder to maintain temperature. To help with that, we place a silicone sock over the heater block. The sock shields the block from stray airflow and helps the nozzle maintain a steady temperature. The amount of cooling required depends on the material and the geometry of the print. The speed of this fan, and therefore the amount of cooling, is controlled in the slicer. Materials like PLA and PETG typically use the fan almost consistently outside of the first layer, while materials like ABS use minimal cooling except for overhangs and special cases. This gets tuned for your specific printer and material using slicer calibrations. All of these components work together to transform a strand of solid filament into precise, controlled molten material. Understanding each piece makes troubleshooting easier and upgrades more meaningful. Now you can look at any Hotend and understand the full story of what's happening inside.
Heat rising fast, it's a molten show. Filament dripping like it's lava flow. Nozzle spitting art in a perfect row. Got layers on layers, yeah, watch it grow. Precision like a scalpel, I slice through air. Melting that plastic like I just don't care. The bed's hot too, yeah, it's all a flare. Dreams get printed while I sit and stare.